Hello and welcome to our lesson on periodic functions and the sine wave. So let's start with what it means for a function to be periodic. I have an example there, but there are plenty of real-world examples. Like you've probably seen a picture of a heartbeat, something like that, where what's happening is you have a pattern of, if we're looking at this graphically, y values that are repeating over regular values of x, so regular intervals of x. So when you have this pattern of repeating y values at regular intervals of x values, you have a periodic function. So you're going to see graphs that are, cyclic in nature. And we say that those graphs contain what we call a midline. And I'm going to show you what this is in the picture in just a second. But basically, it's going to be a horizontal line that cuts the total height of our graph in half. So we should be able to put a midline in there and see half of the height above it, half of the height below. Again, I'll show you in the picture in just a second. And that half of that total height we refer to as the amplitude of our periodic function. That should make sense. You probably associate the word amplitude with height. And if we're talking about this cyclic repeating pattern of y values, one complete cycle, one complete pattern is, as I just said, a cycle. So one complete pattern in those repeating y values in that periodic function we're going to refer to as a cycle of the periodic function. And the number of cycles that are occurring within a specified interval we're going to call the frequency. And oftentimes when we are looking at intervals of our trig functions, we're going to be looking at an interval from 0 to 2 pi. So we'll often talk about the frequency of our trig functions over that interval. So how many cycles do we see of each of those functions from 0 to 2 pi, which hopefully you're thinking about as our full circle, specifically our unit circle. Okay. Now the last term I want to introduce here before I show you the picture is something called the period of the periodic function. And the period is the horizontal length for one of the complete patterns for one cycle. So how long does it take for that complete pattern or one cycle to happen? We refer to that as the period of the periodic function. All right, so what I have in the picture here is an example of a periodic function. It's actually a sine wave, and we're going to talk more about that. But for now, so you can get some of these vocab terms into the picture. So hopefully you can see how this is a repeating graph. Let's say I started at this point right here, and I just kind of highlighted until the pattern was to repeat. Right here, we're going to see this thing start over, and then this highlight would be looking exactly like the previous highlight, right? So those are what we would refer to as complete patterns. So that would be 2 cycles in this interval. So actually here we could say over the interval from negative 2 pi to positive 2 pi, we have a frequency of 2. We see 2 full cycles happening in there. Okay, so this would be 1 cycle, for instance. 1 cycle, and then the pink one would be another. But again, what you're going to see, and the reason we see this pattern happening is because the y values are repeating. So if I'm just going over regular intervals of x values, we have, I'm just going to focus on the y values here. A y value of, this is what, 2, and then up here we have a y value of 4, and then we have a y value of 2, and then we have a y value of 0, and then back to 2, and now you're going to see the same thing repeat. It goes up to 4, back to 2, down to 0, and then up to 4. And if we were to just keep following this forever to the left, forever to the right, we're going to see the same pattern of y values repeat. So again, that's a periodic function. In this picture, we see a frequency of 2. So over the interval from negative 2 pi to 2 pi, we see 2 complete cycles. And the horizontal length of one of those cycles, how long it took for one to happen, we're going to call the period. So if I'm looking at this one cycle that I highlighted over here in yellow, the horizontal length, how long it takes for that to happen in terms of the x values, either you can look at that from negative 2 pi to 2 pi, but it might be easier over here to see that 0 to 2 pi interval. We would call that the period. So the period would be 2 pi, because that's how long it takes for one of those cycles to happen. And then the last term I want to introduce is, or two actually, we have a midline. We said a midline would be a horizontal line that's going to cut this total height in half. So if I'm talking about the total height, the lowest y value I saw there was 0, the highest was 4. So the total height of this graph is 4, which means our midline should be at 2. right in between 0 and 4. And so you can see the midline here. So that's the midline of the graph. And since the graph goes 2 units above that, 2 units below, or half of that total height of 4 is 2, we would say that the amplitude in this graph, the amplitude for this periodic function is 2. And this midline would specifically be at a y value of 2, so we would say y equals 2. Okay, so a lot of terminology, but hopefully not anything too crazy in topic, and some of this terminology is going to come back in. The type of periodic function that we want to focus on for this lesson is one we call the sine wave. So what we just looked at is an example of a sine wave, but I want you to see where these sine waves are coming from. So when I say sine wave, what do I mean? The sine wave is really just a name for the graph that is produced when we're looking at the function or graphing the function y equals the sine of x. And sometimes you're going to see x be replaced by theta, which will make sense in just a minute, but we're going to make a graph. And the graph of this sine curve that we're going to make here, oh, and you saw a word interchange there too. Sometimes I call it the sine curve, sometimes I call it the sine wave, so we use those interchangeably. We can read this or our table of values or the graph we're going to make here in the same way that we can read the unit circle. And since we're new to this, or maybe you're not, but I'm going to pretend everyone's new to this, okay? Anytime we're trying to graph a function, like you probably remember at some point in your math careers graphing lines, right? When you graph a line in y equals mx plus b format, like you can make a table of values to graph that, but eventually you know m and b can be used as shortcuts to graph, right? So there are shortcuts to graphing, and we'll talk about some of those eventually here. But we're going to start by making a table because it's one way we can use to graph any kind of function that we're looking at. So when we go to make our table, and we're going to focus here from 0 to 2 pi, we're just going to go one rotation around the unit circle, and you're going to see why. We can read the unit circle and the graph we're going to make basically the same way. So our x's here are going to be angles, right? We take the sine of angles. So our typical x values are our inputs, right? So not a typical input here. In this case, our inputs are going to be angles. And what are the outputs going to be? So if I put an angle in here, the output's going to be the sine of that angle. So outputs are values for sine. Sines of the angles. Okay? So remember when we're looking at the unit circle that the coordinates for each of the angles that are on the unit circle, these coordinates are showing us a couple of things. We said that the x value in the coordinate is going to be the cosine for that angle, and that the y value is going to be the sine. So we're going to use the unit circle and pick out some coordinates here. Okay, so our inputs, x values, are going to be angles. Let's start at 0. If we're at 0 degrees or 0 radians, we can see right here that our sine value is also going to be 0. And then if I move up here at pi over 6, we're looking at a half. Well, I don't want to graph that. I don't want to graph fractions if I don't have to. And the same with pi over 4 or 45 degrees. I have radical 2 over 2. I definitely don't want to graph that. And pi over 3, we're at radical 3 over 2. I definitely don't want to graph that. Although we can see the values are increasing, right? The y values are increasing because the y values are getting higher. But I'm going to skip to here at pi over 2 because we have a nice y value. So at pi over 2 radians, or 90 degrees, remember those are the same thing, I have a y value of 1. And then once again, when we turn the corner here, we're going to start decreasing. The graph's going to get lower, so these y values get smaller. But here we're at radical 3 over 2, and then here radical 2 over 2, and then a half, and I don't want to graph those fractions or decimals if I don't have to. So I'm going to skip to at pi radians, or 180 degrees, our sine is going to be 0. And then again, I'm going to skip all the way around to this 3 pi over 2. 3 pi over 2, 270 degrees, we can see that the sine value is going to be negative 1. And then I'm going to skip all the way around to, let me get rid of all this mess I made on my, okay, so we said 0, 0, pi over 2, 1, at pi, 0, 3 pi over 2, negative 1. And then if I go back full circle to 2 pi, that's the same thing as 0. And So at 2 pi we get back to 0. You would see I could keep going around the unit circle as many times as I want, right? So I've got a full 360 now. I could add another 90 and get this same y value, add another 90, get the same y value, add another 90, get the same y value, and then just keep going around the circle and repeating that same pattern of y values. So I'm only going to graph here from 0 to 2 pi because it captures one cycle of this periodic function. So now when we graph these, it's a little strange. Normally we just have x values, whole number x values that we're looking at. Here, we're talking about our x values being angles, and although we could do this in degrees, we typically do this in radians. So I'm going to go from 0 to 2 pi on the x-axis, and I went by every 90 degrees was a half a pi. So I'm going to do that here. I'm going to call this a half a pi, these sort of darker increments on my graph. This would be my 1 pi, and then this was 3 pi over 2, and then let's call this 2 pi. Okay, so those are the four major values, so 5, including the 0 in my table. So we said the sine of 0 was 0, make a point there. The sine of pi over 2 was 1, so we make a point there. The sine of pi is 0, so back down to the x-axis. At 3 pi over 2, we're down to negative 1, and then at 2 pi, we're back to 0. And then if I just kept going around the unit circle, that same cycle would continue. And if I went the other direction, so to negative angles, that would take us into the other quadrants that I snipped off this graph, we would have the same thing happening. So this is what one cycle, if we connect the dots here, oh, that was kind of bad. Try that again. Connect the points here. We can connect these because there are sine values in between the ones I chose. I just didn't want to graph them. But in between 0 and pi over 2, we saw these increasing, so we see the graph increasing here. And then after pi over 2, the graph was, the y values were going down, so we see the y values going down, the graph decreasing, and that was continuing around here, right? Decreasing here, and then once we turn, we're going to increase again. So that's the same kind of thing we see happening on the graph, right? We start at 0, then we increase, and then at 90 degrees we turn, decreasing into quadrant 2, decreasing into quadrant 3, and then we turn at the 270 mark, and we're increasing until we make the full circle. So hopefully all this picture makes sense, okay? So this is what our sine wave, our sine curve looks like. This is the graph for y equals the sine of x. And that is what we call the parent form of our graph. So this is the parent form. And maybe that sounds familiar from like your college algebra class. You talk about a lot of parent functions in that one, like y equals x squared is the parent quadratic function, or y equals x is the parent linear function, or y equals the square root of x as the parent square root function. So there are tons of those, right? We want to distinguish, though, between the parent form and then transformations of that parent form. So let's talk about the parent form and its characteristics, and then we'll see how some of the transformations can affect it. So some characteristics of the sine wave, the sine curve, that's the graph produced by y equals sine of x in parent form. So I'm going to say y equals the sine of x, again, parent form. This graph represents a periodic function, and we would say that it is a continuous graph over its entire domain. So as far left and far right as we can go, we are going to see a graph that just continues, which means I could, trace it with my pen or my pencil and never have to lift it, and I could continue along that graph. There are no like asymptotes or holes in the graph, nothing that's breaking up that domain. So we would say it's a continuous graph over its entire domain. The amplitude, remember the amplitude is half of the total height. Let's go back to the picture real quick here. The total height of this graph is 2 units, right? The lowest is -1. That's the low point on the graph. That's the smallest y value we saw. The high point being 1. That's the highest there. Means again our total height is 2, so we have 2 units, and I don't know how far. Okay, so the midline, and I should have drew this when we were here earlier, would be technically the x-axis. That's our midline, and if we're going 1 unit above that, 1 unit below that, we'd say the amplitude is 1. Or again, half of that total height of 2 would be 1. That's our amplitude. Okay, so we're going to say the amplitude is 1, and the period, again, sorry, back to our terminology, was the horizontal length for that one cycle? Well, it took one lap around the unit circle for all those y values to start repeating again. So we're going to say the period is 2 pi. Again, that's the standard. And then we saw the maximum, and when I say maximum, I'm talking y. Maximum y value was 1, that's the maximum output. The minimum output, minimum y value was -1, so the range is the word for our y values, goes from -1 to +1 inclusive, so we're going to put brackets on that. And domain, really the angles that we could input could go on forever, so we see that infinite domain. But it's also important to note on our sine wave, because this will be different when we get to our other trig functions, where it crosses the x-axis. So I'm sorry for this page flipping, but if we look where it crosses the x-axis, what we're looking at are y values of 0. So those y values of 0, when we get back to the x-axis, so again, back on the x-axis, or the x-axis here where I put my midline, that happens when we have y values of 0. So we had it happen at 0 pi, at 1 pi, at 2 pi. And then if we just keep going around, every time we get another 180 degrees, another pi radians, we're going to see it touch the x-axis. We're going to see an output of 0. So we're going to say, to generalize this, that the x-intercepts are in the form, that's my highlighter, n pi, where n is an integer. So we saw it cross the x-axis. We could see it if we went backwards. I just cut the graph off. So we could say at -3 pi, at -2 pi, at -1 pi, at 0 pi, at +1 pi, 2 pi, 3 pi, and so on. So if we were to just keep graphing that at every multiple of pi, where the coefficient there is an integer, we're going to see the graph touch the x-axis. We're going to have a sine value of 0. And then one last little detail, get a little review from college algebra. We would call this an odd function. An odd function meaning that it has symmetry about the origin. And that's sort of a hard one to visualize for some people. So let me show you a couple things in Desmos real quick here. So if we had a graph like y equals x squared. Hopefully we know this picture. This is a graph that we would say is even. An even graph has symmetry with the y-axis. So you can see the y-axis as a line of symmetry. If you fold it over that line, the two halves of your parabola are going to match up. Okay? So when you have an odd function, you have something like y equals x cubed instead of y equals x squared. This is a type of function that we say has symmetry about the origin. Now in plain speak, how I like to describe this to people is, when you have symmetry about the origin, the graph contains every point and its opposite. So for example, there would be a point on this graph at 1, 1. Its opposite would be -1, -1. Change the sign of the x and the y. So what you can see here at -1, maybe I can't get there because my fingers, as the cursor, is not so accurate, but you saw it for a brief moment there at -1, -1. So every point in its opposite. And you could see that in a table of values, right? If I input -1 as an x value, -1 cubed would produce a -1. If I input +1, I get a +1. If I input 2, I get 8. If I input -2, I get -8. So every point and its opposite sign basically is what happens. So if you were to input a negative, then you're going to get a negative output. And so we could say, if it's odd, it has symmetry about the origin, inputting a negative makes your output negative. Okay, so that's what's happening with our sine function, our sine wave. All right, now again, some more details with the calculator. Let me go here. You should be able to graph these things by hand, and you're going to get good at it hopefully eventually, but I also want you to be able to use technology to graph. So if I wanted to graph the sine wave that we just looked at on the other side, just the parent form, when I type it in here, y equals the, oops, not what I wanted, the sine of x, then we see the picture, but since this is in radians, excuse me, and since our inputs were angles in those radians, I want to make my x-axis match. So instead of using these real numbers here, or just, real, irrational, however you want to describe these, instead of a normal axis going from like negative 10 to 10 and in increments of 1. I want it to be how I graphed it just a second ago. So I specifically wanted to look at one full rotation of the unit circle, so from 0 to 2 pi. So that's what I'm going to do on my x-axis. I'm going to say just let the x-axis go from 0 to 2 pi. And I went every 90 degrees, every pi over 2 radians to take a nice specific point in my table. So I'm going to do that here as well. So the step, those are your increments along your x-axis. So I want to go pi over 2 radians. And then the y-axis, I don't really care, but you can make it like negative 5 to 5 because your outputs could be those integers. And increments of 1 there I think would be fine. And we're in radians, so then if we zoom here a little, you can kind of see the same picture. So 0, 0 we said. At pi over 2 radians, we had a max of 1, then back to 0 there. And there was our minimum of negative 1, and then there's our back to 0. So there's what one complete pattern would look like. So now I want to look at a couple of, again, review items maybe from college algebra. Like what happens to our graph if we are to multiply by a negative. So if I put a negative here, it should make sense what's going to happen. It's going to take all of our outputs and make them negative. So if I make 0 negative, that's not going to change. But if I make 1 negative, then instead of having our, at pi over 2, instead of having a maximum there, that's going to flip that over to make it a negative 1. And then the minimum at negative 1, that's going to flip and become a positive 1. So that negative, making all of our outputs negative, does this. Let me go ahead and put this in Desmos so you can see it. It reverses our graph. So instead of starting at 0 and then going up to that maximum, we start at 0 and we go down to our minimum. And at pi, we still hit 0. At 3 pi over 2, again, instead of being at our minimum, we're now at our max. But we don't see the intercepts change. We just see it reflected over the x-axis. And hopefully that makes sense. It's the same thing that happened to all of our other parent functions in college algebra. So this reflects the graph over the x-axis. So if I was to sketch this graph, and this is good practice, again, I'm going to go in increments of pi over 2. So then this would be pi, this would be 3 pi over 2, and this would be 2 pi. Or if you're thinking in degrees, 90, 180, 270, and then 360, like our quadrantal angles. Okay? So sine starts at 0. That's also important to know because it's going to be different when we look at other functions. The sine starts at 0. Normally would go up to its max of 1, but because we reflect, it's going to go down to the min of 1, and then it hits 0 again, and then it goes to the max, and then we hit 0 again, and there's our one complete cycle. So one complete cycle from 0 to 2 pi, just reflected over the x-axis because we put a negative in there. Okay? What do you think is going to happen if we do this? This is one that we probably know from college algebra as well. If we double all of our outputs, right? That's what's happening. We're taking the sine of some angle, and notice there's an x or a theta here instead of an x. It doesn't matter because our x's represent angles, so we can use that variable. But if we take that sine of our angle and then double it, should make sense that all of our outputs are doubled. So let me show you in Desmos. Let me take the negative out and put a 2 in here. So now instead of our maximum being 1, we can see our maximum at 2. And instead of our minimum being negative 1, our minimum's at negative 2. Right? The x-intercepts didn't change. The fact that we have one complete cycle from 0 to 2 pi, that doesn't change. What changed now is our max and our min. So technically what we've doubled is our amplitude. Right? Instead of going from negative 1 to 1, now we're going from negative 2 to 2. We've also doubled that range. So this, multiplying by 2 out here, this doubles the amplitude. And imagine if you put a 3 there, you'd triple it, put a 4 there, you'd quadruple it, put a half there, you would cut it in half. Okay, so again, this would be pi over 2, pi, 3 pi over 2, and then 2 pi. Sine's still going to start at 0, and we always go up to the max. The previous one didn't because it was reflected, but this one isn't. So from 0, we're going to hit our maximum, which this time will be 2, and then we're going to hit the axis again. And then at 3 pi over 2, we'll hit our minimum, which now will be negative 2, and then we hit the axis again. So now one complete cycle looks like this from 0 to 2 pi. Okay? And then I want one more I want to show you here. If I, instead of multiplying, and that, sorry, let me go back to this one, doubles the amplitude. In college algebra, you talk about this as a vertical stretch of the graph. If you just took your graph and stretched it vertically, that's still the same thing that would happen if you were looking at y equals x squared versus y equals 2x squared. You stretch it. But because we have terminology here to call that distance that it stretches, we call it the amplitude. I want to specifically mention that here. Okay. Now let's go to this one. And I don't know how many college algebra teachers talk about this transformation. I know I don't in college algebra. I talk about multiplying the entire function by 2 or by a half, or like vertically stretching and compressing. The 2 in this case is not going to do the same thing. It does either vertically, or does either stretch or compress, but it's not vertically, it's horizontally. And that should make sense. This one is connected to outputs. This one is connected to inputs, so it's going to change the happenings of this graph horizontally, where our inputs are. Now let me show you. I'm going to take this 2 away, I'm going to put it here instead, and maybe you can see what happens. So maxes and mins, still 1 and -1, but I don't know if you can tell what's happening. Instead of one complete cycle in the graph, we see 2 of them. So you can see it hitting the maximum twice instead of just once. You can see the minimum twice instead of just once. And here we're hitting the axis 3 times, and here it is again 3 times. Like, this is 2 complete patterns there, 2 cycles. So we've doubled the frequency. Instead of 1 cycle from 0 to 2 pi, we see 2 of them. And so that's what's going to happen when we multiply x here. Again, we're changing along the x-axis, not the y-axis. So this doubles the frequency. And guess what? If I put a 3 there, then we would see 3... I can't spell. I'm trying to talk and write at the same time. We would see 3 cycles, frequency, from 0 to 2 pi. If I put a 4 in there, we'd see 4 cycles from 0 to 2 pi. So we'd say the frequency change when we change that number. If I put a half in there, we're going to see half a cycle from 0 to 2 pi. So now let's try to sketch this. This time, my axis is going to have to change. So, let me get back to my picture here. One of my cycles completed at pi, and the second one completed at 2 pi. So one cycle has to fit in here from 0 to pi, and the second one from pi to 2 pi. Okay? So if we're going to do one cycle here, then remember, we start at 0, technically we end at 0, in the middle we hit 0. And then in between the zeros is where we hit our max, which was 1, and our min, which is -1. So there's 1. And now I got to do that again from pi to 2 pi. So in between we hit 0, and then in between the zeros we're going to hit our max, and we're going to hit our min. And now I can sketch this in, and you see kind of how nice it is to be able to do this without having to make a table, just using maxes and mins and knowing how many cycles or what the frequency is for our graph. Okay, so you'll get some practice with this, but hopefully you're feeling alright with it so far. So now I want to talk about not just the parent form, but the general form for a sine function. So we still have our parent in there. There's our sine of x. But what happens when we introduce some factor here and a factor here? Then we should be able to know basically what's going to happen to the graph in the same way when you're looking at x squared plus 1. You know the graph shifts up 1 or whatever. We got to know what these a and b, what these things do to our graph. So first, when a is positive, so your sine graph always starts at 0. When a is positive, then the graph goes up to its maximum from 0. When a is negative, and I don't know why I made it capital over here, then instead of going up to the max, it goes down to the minimum because it reflects over the x-axis. And then the absolute value of a, so like if there's a 2 here, not only is it going to go up, but it's going to go up to 2. If there was a -2 there, then it's going to go down to -2. So that number not only is going to tell us if we're going to go up or going to go down from 0, it's also going to tell us the amplitude. How far do we have to go up, or how far do we have to go down? So what is that, max or min? It's sitting right there. And then b is going to show us the number of cycles that are happening from 0 to 2 pi. And the number of cycles, remember, we're calling that the frequency. So b is directly affecting that frequency. And then another question we're often asked is, what is the period? So how long does it take for one complete cycle to happen? So let me go back to this one here where the frequency changed, because this was one cycle that happened from 0 to 2 pi, one cycle that happened from 0 to 2 pi. So the period here is 2 pi. The period here is 2 pi, and that's the standard. That's what's happening in our parent form. But over here, when we change the frequency, we're changing the period. So the period, remember, is the horizontal length for one cycle. So one cycle didn't take 2 pi to happen. This one cycle happens over pi. So this one, the period is pi. So in general, how do we figure out what that period is without having to look at the picture? Well, it's directly affected by that number, by b. So we're going to say, erase this. Oops, that's supposed to be erased for a second. We're going to take our normal period of 2 pi and we're going to divide it into how many cycles do we have to fit into that 0 to 2 pi. So if I divide by b, in this case 2 pi divided by 2, I can see that one cycle is going to happen in pi radians. So in general, if I want to find the period, I take the standard, where we always start, 0 to 2 pi, that 2 pi, and divide it by b, because it's going to tell us the frequency, how many cycles we got to fit into that 0 to 2 pi. So the period, that's the length it takes for one cycle, is 2 pi divided by b every time. So then we should be able to look at some equations and know things about the picture, and we could confirm with our calculator, but hopefully we don't need it. So when I'm looking at this y equals 4 times the sine of 1/3 theta, I know several things. It's a sine wave. It's going to have to start at 0. It's going to have to end at 0. It's going to have to 0 in the middle. But because there's a 4 here, I know some more. Because it's positive 4, it's still going to go up. And it's going to go up to positive 4. So if a is 4, so first, let's say a equals 4, that tells me that the graph goes up from 0. And then it also tells me that the amplitude is going to be 4. So it goes up to a max of 4, and then it's going to go down to a min of 4. And then here, I also have b as a third. So what does that tell me? So b is the frequency, okay? It tells me there's going to be 1/3 of a cycle from 0 to 2 pi. Okay, only 1/3 of a cycle is going to be fit in there. So then if I said, what's the period, you could tell me how long it's going to take for a full cycle to happen. Well, if I take 2 pi and divide it by that 1/3, 2 pi divided by a third is 2 pi times 3. It would take 6 pi radians for the whole thing to happen. And that should make sense. Only a third of it's going to happen from 0 to 2 pi. So the second third happens from 2 pi to 4 pi, and the third of it happens from 4 pi to 6 pi. Okay? Hopefully all that's making sense. Let's look at the second one. In the second one, we see a equal to -5. Again, I know this is going to start at 0, end at 0. Now I know if it's a -5 that the graph is going to go down from 0. It goes down from 0. It's going to be reflected over the x-axis. Can't talk and write at the same time. Struggle. Okay, so down from 0. And then when it goes down, it's going to go down to a minimum of -5. And then when it shoots back up, it's going to go to a maximum of +5. So we're going to see an amplitude of 5. Max is 5, minimum is -5. And then here in this one we have b equal to 4. That means we have a frequency of 4. That means we're going to see 4 cycles from 0 to 2 pi. So they would be really small cycles, right? If we had to squeeze 4 of them in where we normally have just 1, again, we're going to take the 2 pi now, divide it into 4 cycles. That means one cycle is going to happen every pi over 2 radians. So every 90 degrees, we're going to see a full pattern happening. Okay? And then if I was to go in reverse, like here's the picture. What can we say looking at the picture? So again, we got to know this is a sine curve because we're starting at 0. And because it goes down from 0 toward the minimum instead of going up toward the maximum, I know that a is going to be negative. So how negative is it, or what is the amplitude going to be? Because I see the minimum at -3 and the maximum at +3, then the amplitude has to be 3. And again, because it's going down, all of that tells me that a has to be -3. And then b is the frequency. So how many cycles do we see happening in the 0 to 2 pi window? So if I was to highlight, here is one cycle. Remember, start and stop at 0 and then hit 0 in the middle. So I know I have to start, hit 0, and then stop at 0. So I got to get 3 zeros in there in order to complete a cycle. So there's one. And then I can see a second one here. 1, 2, 3. So again, 1, 2, 3 zeros there. So I can see 2 cycles. B is 2 because there are 2 cycles. So if I know A and I know B, then I can also write the equation for the function here. So I'm going to change colors. Sorry. Put this together and say the equation would be y equals a -3 times the sine of 2x. And this could be confirmed nicely. Let's put a -3 in here. And from 0 to 2 pi, that is, it's a little bit, but there it is. We can see the same picture on Desmos that I see on my paper. Okay? So I want you to be able to do a few things. Look at the graph, know it's a sine curve, know if it's reflected, know what the amplitude's going to be, know what the frequency is or how many cycles you can fit in 0 to 2 pi, and then how that affects the period. So know what the period is going to be. And maybe I'll make a note of that one real quick here. So the period on this one is how long it took for one cycle to happen. One cycle happened from 0 to pi, so the period is pi. And again, you can find that by taking 2 pi and dividing it by b, which was 2. And 2 pi divided by 2 is going to be pi. And actually, let me back that up. So 2 pi divided by 2, which is pi. But you can see it on the graph, right? Right there. 0 to pi is how long one took to happen. So you should be able to read those things from a graph. You should also be able to read all of those things from the equation of the function. And then, yeah, I think we're going to be good. So remember, all of these characteristics are applying to the parent, but we should know how to transform the graph in terms of reflections, and then vertically and horizontally stretching or compressing. Okay, so I think you have enough to get started on your assignment, but as always, if you have any other questions, feel free to reach out. Until next time, take care.